Hey, we got another integral here. This one's from UNSW Integration Bee 2019, problem number 17. We have the integral from 0 to pi over 2 natural log tan x dx. Okay, and what I want to notice, our bound from 0 to pi over 2, and with a trig function, that allows us to use a substitution that works quite often in a contest problem. So what we can try is, we can set our u equal to pi over 2 minus x. Then just a quick rearrange solving for x. We have x equals pi over 2 minus u. We'll take our derivative, and dx is going to be minus du. Now we're just going to do our substitution and see how it goes. So if we plug a pi over 2 in here, we're going to have a 0 on top, and then we plug a 0 in, we're going to have pi over 2. We'll have our natural log. Tangent of x is going to be just pi over 2 minus u. We'll have our minus du. What I'm going to do with this minus sign, I can actually bring this outside the integral. So we'll just show that as a plus, and we'll use that to change our bounds here. So we'll just switch it back. This allows us to flip our bounds back to the way they were originally from 0 to pi over 2. Next, on this tangent right here, you'll notice we have for the complementary angle formula for tangent. Tangent of pi over 2 minus u is just going to be the same thing as cotangent of u. If you don't happen to remember this formula, you might be able to remember it from sine, because the complementary angle of sine is cosine. Complementary angle of cosine is sine, and so it's essentially just flipping it and you get cotangent. So what we're going to be able to do here is we're going to be able to just rewrite this here as cotangent of u. And so what I'll do is rewrite this, but what I want to do at the same time in one step is I'm also going to make a variable change, definite integral. So in a definite integral, the variable name really doesn't matter. So we'll change it back to x just to get it back in line with our original integral. So let's see how this is going to look. Okay, so now we're back in x, and we'll do a very common trick with these kind of problems. What we're going to do is add what we have here to our original integral. So we're going to I'm just going to call my original integral I, and all we've done is manipulated it. So this thing here is still I. So if I add this one and this one, we're going to have 2i, and we can add these two integrals together. So let's see how that's going to look when we add them. Now here you notice we have our 2i. I've actually omitted the integral sign here. Okay, but if we have, we could have this integral sign here, but we've got the same bounds and the same variable, so we can just add these two together and have it under one integral sign. And then at this point, the nice thing here is we can actually use this property of logarithms, right? If we're adding logarithms, we can actually multiply what's inside. So we can rewrite this thing as natural log of tan x times cotangent x. But this thing here is really nice because tangent times cotangent is just 1. The natural log of 1 is equal to 0. So what we're saying is we're just integrating 0, and that of course is 0. You could divide by 2 here, right? Because it's 2 copies of the integral, but 0 divided by 2 is still 0. Anyway, fun problem from UNSW. Thanks everyone for watching. Have a great day.